Basic Statistics. We're looking at Chapter 9. Alright, so 9.1, hypothesis testing, difference between two parameters. So the null hypothesis is there's no difference. The alternative hypothesis, which on the note packet, you got to put little ones. They all came out as H naught, but the second row should be H sub 1, H sub 1, H sub 1. So look at my key and fix that, please. Sorry about that. So a little interesting sidebar here. Why is the first thing always called the null hypothesis? Well, let's take a look. If I have one mean equal to the other mean, if I move them over, if I subtract mu2 from both sides, mu sub 2, I get it equal to 0. So the difference between the two is null, the null hypothesis. That's the origin of why we call H naught the null hypothesis. So, and then H sub 1. Again, I should tell you, sometimes books, instead of H sub 1, will put an H sub A, like a alternative hypothesis, the null hypothesis, and alternative. They never use an H sub n there for null. It's always H0, but that's sometimes an A instead of a 1. This book goes heavy with the 1, so that's why I'm usually demonstrating it like the book for you. And then that could be not equal to, or it could be greater than, or it could be less than. So not equal to would be a 2-tailed test. Greater than or less than would be a 1-tailed test. All right. So let's take a look. Population 1, USA. Population 2, Canada. Null hypothesis. 5 years greater than the average lifespan. Equal in Canada. I think it's the other way around. Okay, so that's about it for section 1. Is just kind of going through independent, dependent. Independent means they were random samples taken from, two different populations. Dependent, we're going to look at that in chapter 9 eventually also, but that's paired data. That's like a before and an after thing, like a diet supplement or something. All right, so let's take a look at 9.2, page 2. Test the difference between two sample means using the z-test. Test the difference between two sample means using p-values. Again, we're not really going to do the p-value thing very much. If you're in z land, you can look at the p-values, but other than that, in t you can't, and chi-square you can't without the use of the technology, the calculators. So we're going to stick with the z-test mostly. So let's see. Page 2, jump down to the bottom. Conditions. The samples are independent. There is no interaction overlap for the subject selection in each sample. Standard deviations of both populations must be known. So just like before, we need a normal population, or n is greater than 30 on both of them, and we need the sample, the population standard deviation. If you're going to use z, if you don't have the population standard deviation, you have s instead, the standard deviation of the sample, then you have to use t, the t distribution. So just like before, only this time we're comparing two populations. All right, so let's take a look at page 3. They have the formulas there, and let's do a problem. So what does this look like? We've got men and women, males and females. And the sample of men is 40. The average days until they were promoted was 170. and the standard deviation of the population was 18. So they gave you the population standard deviation. So that was sigma. All right, we put little sub 1s on all of those. So that means the population 1 was the men. All right, the women, we'll call that population 2. So N sub 2, X bar sub 2, and sigma population sub 2. And so for that, we had 50 women in the study and 187 days. You know, it's clearly more, but we have to see, is it significantly more when the standard deviation of the population is 18? And we'll set a level. Ooh, they're setting a pretty stringent alpha is 1%. So that's it's got to be, that's a pretty strict level. All right, so let's take a look. The null hypothesis and the alternative hypothesis. And so this is just saying the populations. Don't say x sub 1 and x sub 2 are equal. We know those aren't equal already. We're trying to make generalizations about the population. So the population of men is equal to the population of women. There isn't a difference in promotion, time of promotion. Or it looks like we're testing that the way it's written, I initially, and I just went with X bar. I'm going with mu. We're making generalizations about the mu. The way it's written, it says, test the claim the average time to promotion is greater for women than for men. So when I first wrote this out, you can see I scribbled it out on the notes. Sorry about that. I wrote mu sub 1 is less than mu sub 2. But instead I decided, now that wouldn't be wrong. If you did write that, I wouldn't mark it wrong. That's fine. You're just kind of redoing it. I'm going to keep it the same as how they had it worded. That women, the time for women to get promoted is greater than the time for men to get promoted. So I'm doing the old switcheroo there, all right? Again, it wouldn't be any different. There would be a slight difference in that when you looked up the Z. So we're going to get to use Z, the Z statistic for this one. And it's going to be on the top end. So if you would have stated it the other way, that men take less time, so mu sub 1 is less than mu sub 2, it would just be shaded down here and you'd have a negative on your critical value. So the critical value for Z, it's a Z score, we look it up, for 1%, one tail, 1%, we follow it all the way to the bottom, and so that's a little different, 2.326. It's not as common as the other ones that we always run into, the 1.645 and the 1.960. All right, so now we have to find the statistic. So here we go. So Z is equal to the difference. So 187 minus 170, because I put that one first and that one second. I put 187 first and 170 second. It's going to be positive here. If I had them flipped around and it was negative, then I would have put the 170 first and it would have been negative. It still would have worked out to the same solution. Oh, also they have this in the formula. Let me write the formula up here for you. So it's on the note packet. X bar 1 minus X bar 2 in parentheses minus mu 1 minus mu 2 over the square root of the variance over the first population size plus the variance of the second over the second population size. So those do get paired. That's how to find Z. So it does get paired. The first population with the n sub 1 with the standard deviation, well actually the variance, the standard deviation squared, and the variance of the second population with the size of the second population. Now in this case, they said 18 was the population standard deviation for both. So that's why we got to use 18 twice. They can be different though. All right, so this is always 0. Remember I talked about the y sub 1 minus y sub 2 is equal to 0. That's the null hypothesis. If we just subtracted that algebraically over to that side, it would be equal to 0. The book, you might even see the hypothesis stated like this in the book. These are interchangeable. I usually just stick with that. Keep it simple, silly. So that's what we do with that, but that's always basically going to be 0. So if you want, you don't even really have to put that part into your work. I don't really need you to always say -0 there, unless you really want to. All right, so now we got 18 squared divided by 40 plus 18 squared divided by 50. And that's all under the square root sign. So 18 to the second power divided by 40 plus 18 to the second power divided by 50. It equals, that'll actually give you, let's see, 17 over the square root of 14.58. And then you take the square root of 14.58. And that is 17 over 3.818. Which is z-score of 4.452. Whoa, 4.452. Standard deviations above the mean. So we had to beat, basically the number to beat was 2.326, and we beat that easily, handily, right? That's where my z-score ends up well into the shaded area. That means we reject the null. We conclude the alternative. So letter D, reject the null hypothesis at the 1% level. So that was hard to hit, but we hit it pretty easily with this data. So there is very little possibility that the generalization that this should be looked into. It's for sure not equal to. Women are taking longer to get promoted than men in this company. All right, so reject the null at the 1% significance level, and then we make the conclusion there is evidence to conclude that the average number of work days to promotion is greater for women than for men. So the average number of work days to promotion is greater for women than for men. Okay. All right. So let's look at a couple more examples. One where we do another build up here, and then another one where we do the confidence interval, a 90% confidence interval. All right, so let's take a look. Instead of erasing everything here, I'm gonna save some of my work because this really works out to be very much the same over and over and over again. That's going to change a little bit. That's going to change. And we get to find Z again. And no, whatever level. And there is evidence to conclude. So we'll have a different conclusion. But yeah, so that's the upside of these problems. It's the same structure again and again. You just have to know, oh, do I get to use a Z? Do I have to use a T? But the actual testing is all pretty much the same stuff. So let's see, this time it's in a clinical study, 40 random tests that were given experimental drug. 30 were given a placebo. So that's called a control group. The placebo group is the control. Just to see if it's just in your head that you're feeling better. All right. And then, and it's usually double blind, meaning the patients don't know if they're getting the fake one or the real one, and the people giving it to them don't know. All right, so let's see. Where the experiment? So this was the experimental group, and this was the control or the placebo. All right. So null hypothesis: there is no difference in the population. It didn't reduce the time for recovery. And then this one is it did reduce the time for recovery. So the experimental should be less than the placebo, less days, 8 compared to 9. And it is less, but is it statistically significant? Let's see. And this one they set at the 5% level. It's on the low end. So again, you know, here we are, Z, or the critical value, CV, is that negative 1.645. That's what I was saying before, that's like really common, you see it again and again. All right, so this will be a little faster, 8 minus 9. You don't really have to put minus 0 unless you want to. And that's over the square root. Again, they gave us 2 as the population standard deviation for both. So 2 squared over 40 plus 2 squared over 30. So we got negative 1 over the square root of 0.23333. And then that's negative 1 over 0.483. And that's negative 2.07. So when we look at that z-score, negative 2.07, that is in the shaded area again. So here's z, negative 2.07. It's well into the, you know, not as far as the 4.4 was on the other one, but it is. It's in the, so it's reject the null. So we reject the null. We conclude that. So we reject the null at a 5% significance level. And there is evidence to conclude the drug reduces the average recovery time. All right. Okay. So let's take a look at building a 90% confidence interval. So now this isn't going to really be connected to this. I did say in there you could reject the null if it were but it doesn't connect to this experiment. That would be, it would have to be not equal to, and it would have to be 10% significance level for it to connect to a 90% confidence interval. So it says find a 90% confidence interval. So this is just sort of a separate problem, but you know, there could be a connection to it where you can use confidence intervals to make your conclusions. We saw that at the end of chapter 8. But it would have to be coupled with a not equal to. And the one that I just erased was a greater than, not a, or less than. So not a not equal to. So it was only a one-tailed test. Confidence intervals can only be used to make the conclusions on a hypothesis on a two-tailed test. So you need that not equal to there to have those be connected. Okay, so this is how we do it. It's x sub 1 minus x sub 2, x bar sub 1 minus x bar sub 2. And now he has plus or minus. I'm going to write it out the whole thing here. So it's minus. Oh no, I got my minus and my plus mixed up. That's supposed to be a minus. And okay, that was the only thing that was messed up. There's a minus messed up on there. I'll have to re-upload that. So then z and then the square root of sigma squared 1 divided by n squared sigma squared 2 n sub 2. And that, so this is the margin of error. And that's, the middle part is mu1 minus mu2. And then it's this again, x1 minus x bar 2. So that stays a minus, but the plus, and I'm just going to put MOE, margin of error. MO. This is the margin of error. So instead of writing that whole thing out again, those are both, boom, the margin of error. And so that is a shorthand that you'll see on the note packet where they just do plus or minus, and then, you know, it's not as an inequality, then it's just as an interval notation, which you could do. So, okay, let's put in info. Minus 9 minus 1.645 square root 2 squared over 40 plus 2 squared over 30 is less than mu1 minus 2. It's less than, let's do 8 minus 9 is minus 1, and then we're just going to say plus. Okay, so now we did this already above it, right above it. You can just take that same answer. I'll put in the 2.33, and then we do the square root of that, and that's 0.483. And so this is 1.645, this is 1.645, minus, that's negative 1, 1. So negative 1 minus that, negative 1 minus, the margin of error here is 0.7945, which is less than mu1 minus mu2, which is less than negative 1 plus 0.7945. And so then when you combine those, it's negative 1.7945 is less than mu1 minus mu2, which is less than negative 0.2055. So, if we had a null hypothesis that they were equal and an alternative hypothesis that they were not equal, this would be evidence for the alternative hypothesis, because it goes from negative and it stays negative, so it misses 0. So if mu1 minus mu2 is equal to 0, that's the null hypothesis, and it's not included in that. So this is evidence for the alternative hypothesis, as long as that alternative hypothesis looked like this. Look, if we had a null that mu1 minus mu2 is equal to 0, or equal to each other, and an alternative that they were not equal to each other, then this would be evidence for the alternative, because this interval does not include 0. Had that been a positive 0.2, then it would be evidence for the null hypothesis, because then it would go from a negative to a positive, which includes 0. So basically, if this is in the interval, it's evidence for that. If 0 is not in this interval, it's evidence for that. But that doesn't connect directly to the one above, because that was a one-tailed test, not a two-tailed test. All right? Okay. Next notes I will do will be 9.3.